I'm Dino Su. I'm a sixth-year graduate student at UC San Diego. And today I'm going to talk about some ground dwarf kinematics, including NIRSPEC T-dwarfs and lay M's and L's. So here's the outline. First, I have briefly introduce what ultra-cool dwarfs are and their thermal evolution. And then I'm going to talk about what we understand in the past about ultra-cool dwarf kinematics, and then some mystery for L dwarfs locally. And I'm going to talk about the nearby T-dwarf observations with KeckNIRSPEC and our MCMC for modeling pipeline. Then let's move on to what's the update consensus of ultra-cool dwarf kinematics. And I'll propose our resolution for the mystery for the local L dwarfs and kinematic break identify around L4 to L6 subtypes. So let's get started. There's just a quick review of brown dwarf and low-mass star thermal evolution. So this is the thermal evolution that's below 3000 kelvins and versus the log H. And this combines all the M, L, and T dwarfs. That includes, for M dwarfs, it's mostly stars and plus some young brown dwarfs. And if you go to L, there's a mixture of both stars and brown dwarfs. And finally, if we move to cooler temperature, there's all brown dwarfs for T dwarfs. And there's one important feature to note. So they have the inherent Age-Mass-Luminosity Degeneracy, which means if you look at, say, a green line here, you don't know if that's a young brown dwarf or a pretty old field age low mass star. Another thing to note is that when you go to field age, it's pretty hard to measure their individual age unless you identify with associated higher mass primary, for example. With that all being said, it's pretty hard to measure field UCD age, and there's only a few ways to measure in some young moving groups member, for example, or you can find a Y binary that's being associated with higher mass primaries or Y dwarf. But fortunately, as a population, they go with the same physics. There's a Dix heating mechanism that we can use, which is the so-called the age velocity dispersion with a statistical or ensemble age for a population of stars. And the plot here just to show the velocity dispersion for FGK star versus their age. And over time, because given their population encounter certain gravitational interactions, for example, with the giant molecular cloud or bars or arm structure in our Milky Way galaxy, and over time, that gets older and the velocity dispersion goes higher. We can use their ensemble velocity dispersion to infer their ages. And here's pretty much for introduction. And let's talk about a little bit of what we do know in the past for ultra-cool dwarf kinematics and the mystery for L dwarfs. So this is a compilation of all of the brown dwarf surveys, starting from the lay M's all the way to T, and with the ages. So if you just first look at the plot on the left, that's the age being by per survey, and the measure ages on the y-axis with the uncertainty indicated. So if you look at M's, it's roughly around 3 to 5 giga years. So they're roughly consistent, because if you look at L dwarfs, it's widely spread is because of different survey strategy and sample size issues and selection effect. So there's an inconsistent L dwarf age is all the way from 1 giga year and to almost 7 giga years, which is very inconsistent. And for T dwarfs, you might think they might be like young, but this also has like some sampling issue. For example, the largest proper motion survey by Faraday and O 2009, it doesn't have the RV measurements. So it might introduce additional selection bias. And the largest T dwarf survey with 6D, which means we have RV, there's only 70 dwarfs, which means we don't have a complete sample yet, even for T dwarfs, to constrain our understanding for local ultra-cool population to a lowest temperature. So definitely we need more T dwarf observation with more precise RV. And that kind of motivates the need with more T dwarf observation that they can only be obtained on Northern Hemisphere with KeckNIRSPEC. And I'm going to also introduce the MCMC for modeling pipeline. But first, let's talk about the NIRSPEC observation with the T dwarf data. And also, I've compiled some data from COA. Hopefully, you still remember and the memories are fresh. And if you look at this, this is just sample compilation as a histogram per spectral type. And The red is the NIRSPEC data and compiled with our recent observations. And the blue is the precise 6D kinematics with the radial velocity precision better than 3 km/s. And overplotted on the gray histograms is the current identified all ultracool within 20 parsec. And the dashed line is a simulation I'm going to compare with our theoretical understanding later in the talk. And to achieve such nice RV precision into a sub-kilometer per second, we need to have a sophisticated modeling method. And I'm implementing MCMC formatting pipeline called the SMART package. And it simultaneously model, including the effect temperature, surface gravity, but most importantly, RVs and V psi I. And we achieve a median precision of 0.5 km/s for RV and 0.9 km/s for V psi I. And we also found the first 2 RV T-Dwarf binaries, but I'm gonna not focus on them on this talk. So let's move on. If you look at this example fits, so the left plot is the K-band fit, and in order 33 is kind of famous CO band head. People have mentioned this so many times. And the black is the data, and the magenta is a 4 model with tellurics. Without tellurics, is in blue. Sorry, it's pretty hard to see the labels, but the best fit parameters are also showing in blue labels. And to the right is another order in J-band because toward later T-Dwarfs, their emission is higher in flux in J-band. So we focus on the other order around 1.3 micron, and there's a bunch of nice methane and the tellurics to anchor the wavelength. And I have to shout out to surrounding models, which is amazing, improve a lot of methane opacity issues that's been identified in the past. With such precision, we can construct a larger sample area with a precise radial velocity measurements. And let's talk about the T-Dwarf first and then move on to lay MNLs. So for local T-Dwarfs, this is a summary diagram. For those who are not familiar with that, this is basically a galactic velocity space in U and W magnitude versus the V. And generally, from lower right to upper left, it goes from younger kinematic population to older kinematic population. And we identified actually one source in our T-Dwarf sample to be actually a L6, blue L6. So this source is kinematically older, but if we exclude that source, all of which will be authentic sources. And there's 4 kinematically young sources identified in the survey as well, but 2 of which are chance alignments. And the kinematic ages using empirical age velocity dispersion relation is about 3.5 giga-year. And if we want to compare to another sample, okay, it's updated. For lay M's and L's, again, the same sample plot, but now I want to focus on the blue. And here, if you look at the right, it's the same time rate diagram. Sorry, it's a little bit hard to tell. But the red is the lay M's, and the blue is the L dwarfs. And again, lower right is a younger population, and upper left is the older population. And if it's hard to see on because of the projection here, but there's a bunch of kinematic older L dwarfs with some lay M's. And actually, blue L dwarfs has a higher physics fraction. That's about 8% compared to 3% of lay M's. So we realize there's a kinematic older L dwarfs, which is more than even lay M's. Okay, thank you, Charlie.
It's fine on the screen. It's just
No worries.
where we take solutions from the crowd. Anyone?
So on Zoom, it looks bad too.
What's I think it's almost ready. Like maybe 2 main slides. Is it better now? Okay, thanks. Okay, nice. Okay, so again, just a recap. Here's again same summary diagram, but just for LAMs and L dwarfs. But there's a bunch of kinematic older L dwarfs in the sample. This is being labeled in the circles and thin diamonds labels. And there's about 8% L dwarfs that are being thin disk source, thick disk sources. And let's fill the puzzle together. And so what happens here that we think is here. So now I want to again the same sample plot, but now on the left I want to compare with the population simulations incorporating Brown Dwarf evolution model, for example, and star formation history, and that's shown to the right the inferred age versus the spectral type in the violin plot. So the simulated ages in the population is in a left white violin plot, and the inferred ages from simulated population is in the right side yellow violin plot. And observed ages is in the blue dots. As you can see, for LAMs and Ts, they are consistent with the observations and simulations. However, if you look at L dwarfs, which is the open circle and the upper circle there, there's a huge discrepancy compared to our understanding. However, if we remove these thick sources, it brings the age consistent with the LAMs. So that partly resolves the mystery. That's because local L dwarfs has a higher thick fraction. But we are not sure if this is like sample complete or not. But if you take a zooming on this L dwarf, the same plot, but just being per 2 subtypes in L dwarfs, and observe, just focus on observed ages, you expect in general early L dwarfs actually a mixture of lower mass stars and brown dwarfs, and some of the stars will be older in population, plus some of the young population. When you infer the ages, they'll be more dispersed, and therefore you expect they're older kinematically. However, if you go to a certain spectral type, there's a certain threshold to form a star, which requires a certain amount of mass to ignite hydrogen fusion, and therefore later in certain spectral type there will be old brown dwarfs, which are kinematically young. And there's a break between L6, and we think that this kinematic break is because of this end of Stellarman sequence, and that's also another interesting discovery. However, the sample here is about 40% completeness, or maybe 30%. So we have to have more complete sample in order to make sure that is true. And here's the summary. So we present hopefully the largest sample for a T-dwarf ever, 37 T-dwarfs with a sub-kilometer per second precision for both RB and VSI. And then we've kind of resolved the local ultra-cold mystery by compiling the largest sample ever, 172 LAMLT kinematics, and realize there's a higher fraction of acidic sources in the sample. And removal of this will bring the age consistent. And the kinematic break is identified around L4, L6, which is indicative of the Stellarman sequence. And I'll end my talk here and take questions. Thank you.
Questions? You're on Slack? Yeah. What was your question?
Sorry. Yes. Okay. So the question is, there are some binaries identified in the sample, and what are those? So actually, I have a slide to show. So these are two of the systems we found within 37 sample of 37 T dwarfs. And the first one is J1106 plus 2754, and this is a T0 plus T4.5. The period is about 4 years. And for the other one is L7 plus T3.5 J2026, and the combined line is a T0. And the period is 12 years. And we just finished the last sampling last year around September and December. So.
Thank you, Nina. We'll take it to Slack and sorry about the AV difficulties.